All right, guys, so we are doing kind of the second part of part two, or I'm sorry, topic two today. And the first part of it that we're working on today has to do with electron configurations. So once again, this is not new information. There's one little section today that you will not have seen last year, but everything else that we are going to talk about today is information that you learned last year in first semester for in 10th grade chemistry, in advanced chemistry, or whenever you took it. Most of y'all, I think, took it last year. But to start off with, so this is topic two, part two for SL, and we're going to finish the other part of it on Thursday, okay, and Friday. But really quick, I just wanted to kind of point out some of these things here that we're going to be doing today. So today, we're going to be talking about this third bullet, because we're going to be talking about the energy levels, and we're going to be talking about the sub-levels, and we're going to be talking about the orbitals and their shape. So if you guys remember from last year, we learned how to do electron configurations and orbital diagrams. That was the thing where we had like 1s2, 2s2, 2p6. So we're going to be looking at all those sublevels and then the orbitals. And so these kind of four are what we're going to focus on today under the understandings. The first two bullets under there, that's what we'll be doing on Thursday and Friday. That's kind of in the second half of this. And then as far as here of what you guys need to be able to do, the last two bullets today isn't what we're doing. So we need to be able to recognize the shape of the s orbital and then each of the p orbitals. So we'll talk about that in a little bit. And then apply these rules. And we learned all these rules last year: Aufbau principle, Hund's rule, and the Pauli exclusion principle. And we should be able to write electron configurations for atoms and ions up to atomic number 36. So remember that Z is atomic number. So we're going to see it written like that. If they tell us to write the electron configuration for an element, they might say Z equals, and then give us a number. And when they do that, they're telling us, hey, that's the atomic number. So that's the number of electrons that you need to do for your configuration. Okay. And so it says up to atomic number 36. Number 36 is krypton. So we don't have to do any elements past krypton, which is the fourth row, the fourth period. So we're not going to do anything past that. It's not required for IB. But anything up to number 36, up to krypton, you should be able to write the configuration following those three rules. Okay, so that's what we're going to kind of see today. And then we are going to talk about both full and the condensed electron configuration. So the condensed is sometimes called the noble gas configuration because we use the symbol of a noble gas to kind of make it shorter, give it a shortcut, like this example right here. So we're going to talk about both of those. And then we'll look at orbital diagrams where kind of like where we look like this, where we have the boxes and we draw the up and down arrows in them for the orbitals. But we're not going to use, that's not going to be what you'll mostly see. You'll mostly see questions about electron configurations, maybe relating them to the orbital diagrams, but we're not going to have a lot where it's just the orbital diagrams, okay? And then we're also going to talk about two elements that are exceptions, that they don't follow one of those rules that we just mentioned for the electron configurations, okay? All the other elements follow those three rules, but chromium and copper are two elements that don't, and so we're going to talk about their configurations because you need to know theirs and sort of why they're different and why they don't follow the rules. So to recap, okay, and all of this was in your video notes, but I'm going to kind of go through and kind of add in a little bit more information. This is our Bohr model where we have kind of the concentric rings. And so in IB, they like to use, they like to give labels and letters for everything. So when you see the lowercase letter n, they're talking about the main energy level, okay? And so the main energy level, it'll say n equals, and then it'll be a number. So here it goes up to 4. In reality, we know that there are 7 energy levels, but because we're only being required to do electron configurations up to the 4th period corresponds to the 4th energy level. So for our purposes, we're probably only going to ever have to know up to 4, even though we know that atoms obviously do go larger than that. Kind of the key things to take away from here about our energy levels. The N equals 1, that's the first energy level. It's closest to the nucleus, has the lowest energy. As you move further away from the nucleus, your energy increases. And so that's kind of what the next part here is saying. It says, as the value of increases, the energy also increases. So if you're asked to compare, you know, like this N equals 3 to N equals 1, 3 is going to have the higher energy, okay? And that's important because our electrons, when we get down to talking about our configurations, one of the rules, the Aufbau principle, says that electrons always fill from low energy to high energy. So they're always going to start with that first level. They're always going to start with N equals 1, and they'll fill all the sublevels on that one. Then they'll go up to N equals 2, and they'll fill whatever sublevels are available on that one. Then once those are full, then they go up to 3, and they fill the sublevels on there, and kind of so on and so forth. And then that's kind of leading into the next part. So all the main energy levels, they have sublevels, and the sublevels are represented by letters S, P, D, and F. And there's a chart down here where we're going to kind of go over what that means. And then each main energy level, it can hold 2 N squared electrons. So if you need to figure out how many electrons an energy level can hold, this is the little equation you use to figure it out. So for example, let's say I have the 3rd energy level. I'm on the 3rd main energy level. I would do 2 times 3 squared. So 3 squared is 9, and then 9 times 2, that's 18. And if I come down here on the chart, look, okay, it's got 18 on this chart. So that's the little trick if you need to figure out, you know, you can always memorize what's on here. You can memorize that the first energy level is 2, the second one's 8, the third one's 18, the fourth one's 32. But you can also use this little shortcut if you need to figure out the electrons that way. So what's important on here, okay, is you need to know the energy levels, you need to know what sublevels they have, and then this 3rd column, this tells me the maximum number of electrons in each sublevel. The last column tells me the number of electrons total in the entire energy level. So for example, on the first energy level, there's only one sublevel. It's an S, it's 1S is the sublevel. And so any S sublevel will only ever be able to hold 2 electrons maximum. They can only hold 2. So since that's the only sublevel on the first energy level, then that's why the first energy level can only hold 2 electrons maximum, because it only has an S sublevel. If I go up to the 2nd energy level, now I have 2 sublevels. There's an S and a P on the 2nd energy level. And so S still can only hold 2, but a P sublevel, it has 3 orbitals, so it can hold up to 6 electrons. So if I add 6 and 2 together, that's where this 8 comes from. So 8 total electrons on the 2nd energy level. 2 of them are going to be in the 2S sublevel. 6 of them are going to be in the 2P sublevel. And then it kind of just keeps going. So when I get to the 3rd energy level, I have a 3S, I have a 3P, and then I also have a 3D. So I have 2 from the S, 6 from the P. D sublevels can hold up to 10 electrons, okay? So then if I add those together, that's where this 18 comes from. And then the last one that we need to know for IB is the 4th energy level. It's got 1 of each. It's got an S, a P, a D, and then it also has an F. So I can see again, the S is 2, the P is 6, the D is 10. The F sublevel can hold up to 14. So when I add those, that's where I get a total of 32 for the whole entire 4th energy level. So you kind of need to know these numbers, how they relate. And so that's what kind of the next part has, is it just has a summary. So it says any S sublevel can hold a maximum of 2 electrons. So it doesn't matter if it's 1S, 4S, 5S. If it says a letter S, that can only hold 2 electrons. For the P, a P can hold up to 6 electrons. A D can hold up to 10. And an F can hold up to 14. Okay. So we need to know how many they can each hold, because that's going to impact how we write our electron configurations in a little bit later. Okay. Because for example, like I can't have 3P7 because P can only hold up to 6. Okay. So some of the rules for these, and this rule is a new one. We didn't really learn about this rule last year, but it's called Heisenberg's uncertainty principle. And basically, what Heisenberg did is he did experimentation after Bohr's model. So after Bohr had his model of the atom, where, you know, we assumed it was those concentric circles and those were the energy levels where the electrons were traveling. Well, Heisenberg's experimentation and his research with electrons basically proved that that Bohr model is very limited and it's really not accurate. Okay, so we typically still use Bohr models to draw atoms on paper because it's a very simple way to draw them on paper 2-dimension, and it's easy to understand, you know, all the concentric rings and all that stuff and how many each level can hold, but it doesn't work for most of the elements once you get above a certain number. Okay, in fact, it really only works for hydrogen, and then it works kind of for some of the other lower number elements. And so basically what they discovered is that the electrons are not in these circular paths, they're actually in a 3-dimensional cloud area, and we call those the orbitals. And so the atomic orbitals, and so what Heisenberg's uncertainty principle says is it says that the velocity and position of an electron cannot be simultaneously measured with high precision. And so to translate that into like words that we could understand, basically it means that we cannot know where an electron is and how fast it's moving at the same time. It's literally, it's impossible, scientifically speaking, to know where it is and how fast it's moving at the same time. So velocity is how fast it's moving and position is where it's located, okay? And the reason is because the electrons are so small, because remember they're like 2,000 times smaller than a proton and neutron, and those are already really small. But what you need to keep in mind is that they're so small and they move so fast that we never know where they are at any point in time because they're moving too fast and they're so small. But if we were somehow to like freeze the atom in place and be like, oh, look, there's an electron right there. Well, okay, now we know where it is, but we stopped it. It's not moving anymore. So now we don't know the velocity. We don't know how fast it's moving. And so that's what this says, is that there's no way to know exactly where they are as long as they're moving and they're in constant motion. And so really we have what we call these orbitals, which are the 3-dimensional cloud shapes. And they just describe the probability of finding an electron in an area of space. And so an orbital, it's a 3-dimensional cloud shape, and it's centered around the nucleus. And it says it represents the region around the nucleus where there's a 95% chance of finding an electron. So in 3 dimensions, they have different shapes. So they correspond to those sublevels. So S has 1 orbital, okay, because remember it can only hold 2 electrons. And the s orbitals are spherical. So if I kind of drew a circle around this, I can see that it's a circle, right? But it's in 3 dimensions, so it's actually a sphere. It's not just a flat circle. So this is what like a 1s orbital would look like, and this one is a 2s. So what is different about them? Because they're both round, they're both spherical, but they're not exactly the same. What's different about them? Nope, they hold 2 electrons. That's it. Look at, are they the same size? No. So that's kind of the difference, because remember, as I go up, so this one is 1s, and that means it's on the first energy level. This is 2s, it's on the second energy level. So remember, I'm getting further away from my nucleus. So as my energy level increases, the size of that orbital cloud gets bigger and bigger. And so the region where the electron's going to be is a little further from the nucleus. And so you can tell on these pictures from how dense the little red areas are. On this one, the red area, it's like densest, like closest to the nucleus. But if you look on this one, there's kind of like this ring here. And then if you notice kind of inside there's a lot more white areas, right? It's not as red right close to the nucleus. And so that has to do with the fact that the redder the areas are on these pictures, that's where you're likely to find those electrons. So what you need to know about the shapes of these, you need to know that s orbitals are spherical. Each orbital can only hold 2 electrons. And what you would need to know is that as my energy levels increase, they get larger, but they're still the same shape. So they're still spheres. It's just getting lighter. So it's like, it's kind of like if this was maybe a ping pong ball, and then this one was like a baseball. Okay, so they're both spheres, right? But one is going to be a little bit bigger than the other. And that's because it's the area where the electron is going to be further from the nucleus. And this one has higher energy. So, because remember, energy level 1's the lowest energy. This is on energy level 2, okay, this 2s. So the larger that orbital, that means they're further from the nucleus, which means they have higher energy, okay? So really that's the main difference between like 1s and 2s, or even like if I compared like 1s and 3s, okay? The difference is that the electrons will be further from the nucleus and therefore have higher energy, but they're the same shape and all that stuff. For the p orbitals, there's actually a p sublevel has 3 orbitals, okay? So that's what it's saying down here. The p sublevel, oops. The p sublevel contains 3 p orbitals of equal energy, okay? And the term for that is, they're called degenerate orbitals. So the word degenerate, that just means they're equal energy and they're on the same sublevel, okay? And so for a p sublevel, it's going to have 3 orbitals that look like this. They're clouds. They're called a dumbbell shape. It looks like kind of like 2 balloons that are tied together at the center. And so they call it dumbbell because if I were to kind of take my hand and reach in here, I could pick it up in the center like a dumbbell, you know, like I'm lifting weights, okay? And so since there are 3 of them, this is what they look like because they all overlap. And so they're all arranged at right angles. So you use kind of an axis like you would in math, but it's 3D. So we don't have just X and Y, we have X, Y, and Z. And so you'll have the p orbital that's going in the X direction. You'll have the p orbital that's going in the Y direction, and you have the p orbital that's going in the Z direction. So I'm going to try to kind of draw this all together. Excuse my poor drawing skills. But what this would look like is I would have one of them maybe kind of going this way straight up and down. Then I would have another one that's overlapped and it's going this way. And then the third one, and this is going to be hard for me to draw because I'm drawing flat on paper, but the third one would maybe be like kind of like at this angle. So they all 3 overlap, okay? And my angles are not drawn to scale, but like all 3 of these overlap and the center is going to be kind of at the origin on this graph. They're all 3 overlapping at the same spot. And so each of these can hold 2 electrons. So like the px can hold 2 electrons, the py can hold 2, and the pz can hold 2. So that's why total every p sublevel can hold 6, because each of their orbitals can hold 2. Okay. And they're all equal energy. So we have some rules to follow when we fill them because there are multiple orbitals on a p sublevel. And we're going to talk about that in a little bit later. But it kind of looks like almost like a flower type shape. It's kind of weird looking when you overlap all 3 of them, but they're dumbbell shaped. For D and F, we don't really need to know the shapes of them. We just need to know how many of them there are. So we need to know that the D sublevel has 5 D orbitals. That's why it can hold 10 electrons, because remember, each orbital can hold a pair. So if there's 5 orbitals on the D sublevel, 5 times 2, that's 10 electrons, okay? And it says here you're not required to know the shapes because they're all very, very kind of advanced. They're weird shapes. And the F are even more complicated. F, all we need to know is that for the F sublevel, there are 7 orbitals. And if there's 7 orbitals, that's why it can hold 14 electrons total, because 7 times 2 for each orbital would be 14. Okay. So then we're going to talk about some of the rules for writing these electron configurations. So all these rules, like I said, these are not new rules. You learned them last year, so hopefully this should just be a refresher. The first one, and I kind of mentioned this one earlier, this one's called the Aufbau principle. The Aufbau principle, it states that electrons are filled or placed or filled in orbitals of lowest energy first. So electrons are placed in orbitals of lowest energy first. I like to call this the electrons are lazy rule, okay? Don't write electrons are lazy on your test, okay? If you're asked about the Aufbau principle, you don't write that. You write what I highlighted in yellow, but this is just a trick to remember it, because electrons are lazy. And so if they were to get all the way up here to like 3D, that takes a lot of energy, because on this little chart, the energy is increasing. The lowest energy is down here at 1s, because oops, a little too high. right here past one, underneath 1s, this is where my nucleus is, okay? Because remember, 1s is the closest, that's the first energy level, and the s sublevel, okay? And so if I look, if I go vertical, I get 1s first, then I get to 2s, and then if I keep going vertical, 2p comes after 2s, then I have 3s, then I keep going, there's 3p, and then I keep going 4s, and then here's where it gets weird, because after 4s comes 3d and then 4p. So I start from the bottom, so you can kind of think like you're Drake. You started from the bottom, now you're here, okay? So you always start from the bottom when you're filling your these diagrams, and this is called an orbital diagram, and it's what helps us to write our electron configurations, okay? And so right underneath this in your notes, you have a little thing that helps you to remember the pattern. And what you do is we list all the sublevels. So I list all the S's, so a 1 all the way to 5, and then I can list all the P sublevels, the 3, the D's, and the F's. And so you notice like this row, it's 1, and there's only a 1S. Here there's 2, so there's 2S, 2P, and then here there's 3, so we have 3S, 3P, 3D. And then when I get to 4 and 5, that's now where I have all 4 of them, all the way to F. So I list them like this, and then I do what's called the diagonal rule, okay? So these diagonal lines on here, I start up here at the kind of this top corner, and I go down to the left. And so the first one that I always fill, I always start with 1s, because that's the first energy level, and that's the only sublevel on that energy level. Then I go now down the next one, and I go diagonal there. So after 1s always comes 2s. And then I go up again in the corner, I go down diagonal. So after 2s comes first 2p and then 3s. And then if I have to keep going, then I go up and I go diagonal, then I have 3p and then I have 4s. And if I keep going after 4s, then we have 3d and then 4p and then 5s, okay? And then at that point, that's all we need to do for IB, okay? Because remember, we're not gonna go past number 36, which would be ending in the 4p area. So really, we're probably not ever gonna have to do 5s. But this diagram does keep going. Like you could add the rows down here with 6 and 7 if you wanted to do more elements. But for IB, this is all really that we need to do. So you have to remember this pattern because they always go in that order. And when we do our examples in just a minute, you're gonna see what I mean by that. The other two rules, so the first one, this one's called the Pauli exclusion principle. And basically this one says that no two electrons in the same orbital can have the same quantum number. And quantum number is spin, okay? It represents the spin. So what they're saying is that if I draw an orbital diagram, and remember the orbitals are represented by those boxes like on our diagram above, every orbital can only hold 2 electrons, okay? And they have to spin opposite directions. So when we draw our diagrams, we draw them by representing arrows that point different directions. One goes up, one goes down. And we do these little half or single-headed arrows. So it's not like a regular arrow like this, it's a half arrow like this. So that's the up one, and then if I wanted to do one down, it would look like this. So in a box for an orbital, they always have to look like this with one up and one down. If I have 2 up or 2 down, that's wrong because that is not obeying this Pauli exclusion principle, okay? For the last rule is Hund's rule. And I like to call Hund's rule the share before you pair rule, okay? What this means, Hund's rule says, if more than one degenerate orbital in a sublevel is available, then you have to put them in separate orbitals first. So to kind of summarize that, it says always fill orbitals of equal energy singly with 1 electron, and then add the second electron once each orbital has 1 in it. What that means, okay, this only applies to P, D, and F, okay? This won't apply to S orbitals because S sublevels only have 1 orbital. So notice it says that it's only with orbitals of equal energy, and that's only going to be for P, D, and F, okay? Because if I come back up here and look at this, P has 3 orbitals and they're all equal energy, so it's got 3 boxes. D, and there's actually a typo here, this should have 5 boxes on it, so you can change that in your notes and add that 5th box on there. But D has 5 orbitals, okay, and they're all equal energy. So what Hund's rule says is, Hund's rule says so let's say that I'm filling this up and I start from the bottom. So I've got 1s and I put 2 electrons in that orbital because that's what it can hold. My next highest is 2s, so I'm going to put 2 electrons in that one because that's what that can hold. Once I go up to 2p, let's say that I need to put 2 electrons in here to finish the element that I'm doing. I would do 1 up in the first orbital and then 1 up in the second orbital. That's what Hund's rule says. Okay, I would not do this. I would not do 1 up and 1 down in the first box. That is wrong. Okay, so Hund's rule says, and so that's why I call it the share before you pair rule, because on the sublevels like P, D, and F, where you have multiple orbitals, you have to share. You have to give each orbital 1 electron before you start pairing them up. So if I kept going, my 3rd electron would go here in the last orbital up. Then if I had a 4th electron, then I would come back to the first orbital and I would point it the opposite direction to follow that Pauli exclusion principle so that it's spinning the opposite way. And then my 5th one would go in the second one pointing down. And if I had a 6th one, then it would go down with the last orbital. So Hund's rule is just saying that when in those sublevels where you have multiple orbitals that are the same energy, you give each one of them 1 electron before you start pairing them up. All right, so now we're actually going to talk about writing them. Okay, so again, you did this last year, so hopefully this is just a refresher. But our configurations, they take all these rules, all these information, they put it together in a way for us to represent all this information in kind of like almost like a code kind of, okay? And so we'll have a big number in the front, and that number is our N. That's our main energy level. And then after that would come the letter that would indicate our sublevel. So it'll either be that S, P, D, or F, okay? And then after the letter for the sublevel, there will be an exponent or a superscript, okay, where it's written up high. That superscript or that exponent, that tells me the number of electrons in that sublevel. So the reason it's important we know how many each sublevel can hold is because these numbers can only go to certain amounts. Every time I have an S sublevel, this number can't be higher than 2. It's either a 1 or a 2 because it's either got 1 electron or 2 and then it's full and I got to go to the next sublevel. Okay. For a P, if I have a P orbital, or I'm sorry, a P sublevel, the highest it can be is 6. So it could be a 1, a 2, a 3, a 4, a 5, or a 6, depending on if the P is full or not. For D can go up to 10. So it could be 1 through 10. Just depends on how many electrons we have to put into that sublevel. But it can't be more than 10. And then we probably won't have any of these because we don't have to do it for IB, but F couldn't go up to 14 if you have F. So that's why it's important we know those numbers so that when we write these, we remember, oh, like I can't write 1S3 because S can never have more than 2, okay? The other thing about these is once you write out the entire configuration, if you add up all of your exponents, add up all your superscript numbers, that should equal the total number of electrons for the atom, which should be the atomic number, okay? So this first example that we're gonna look at here, it says write the full electron configuration of the magnesium atom, and then here in parentheses it says Z equals 12. Okay, so remember that Z, as we learned last week, Z is what they use to abbreviate or to stand for atomic number. So if they say Z equals a certain number, that's their way of telling us that's the number of electrons that need to be in our configuration. Because since it's just a regular neutral magnesium atom, that means that protons and electrons are the same. So atomic number for the protons would also be the same as the electrons, okay, as long as it's not an ion. So that means that I need to do a configuration where I have 12 electrons. So I need to go up here to this little diagram. And remember I told you always start up here. So the first thing we're always going to fill is 1s. Okay, I'm going to change color so we can start this. So 1s is first. And how many can an S orbital or S sublevel hold maximum?
2.
2. So it starts with 1s2, right? So then if I go back up to my little diagram, my little diagonal thing, after 1s, I go here. The next one's 2s, okay? And it's another S, so that means that one can also only hold 2. So I'm going to do 2s2. Now, as you're going, keep track of your exponents, okay? Right now, I have 2 and I have 2. That's only 4. I need to get up to 12, so I got to keep going, okay? So if I go back up here and look at this little diagram, the next one I would get would be 2p. So now we have a different sublevel. We're on the second energy level, but we have a p sublevel. So this is 2p. And then how many can the p hold maximum? Yes. So it can hold 6. So I'm going to go ahead and put a 6 and let's check. Like, are we up to 12 yet? If I add these all up. Yeah, we're only at 10 right now because we have 2 plus 2 plus 6. We're adding all those exponents up. So we got to keep going. So after 2p, if I keep following this diagonal, after 2p comes 3s. Okay. So then I'm going to go down here and I'm back to the s sublevel, which means that what's the maximum that that one can hold? 2. Thank you, Abby. So now if I add those up, am I at 12 or do I need to keep going or do I have too many? What do we think? It should add up exactly to 12. I have 2 plus 2 plus 2 plus 6 plus 2, that's 12. So I'm done. Okay, that's my full electron configuration for magnesium. Now, what if they give me, let's do something else. Let's do oxygen. I'm gonna do oxygen. So oxygen, and oxygen's atomic number is 8. Okay, so Z equals 8 for oxygen. So I would start the exact same way. So I know that I would start with 1s, and that's going to be 2. And I might as well just keep going because I know I'm going to have to get up to 8. So 1s, 2 would be first. And then 2s, and that would have 2. So now I'm up to, I have 4 electrons because I have 2 in the first one and 1s and then 2 in the 2s. So I got to keep going. So the next highest one after 2s, if I'm following this diagonal rule, would be 2p. That's the next one I get to. And p can hold up to how many? It can hold up to 6. Now, my question to you, do we need 6 in there? So we're trying to do oxygen. So oxygen, and I told you the atomic number, if I look it up on the periodic table, it's 8. So do we need 6 in there or do we need less than 6? What do we need in there? We only need 4. Okay. So some people get in the habit of they think you always have to put like 2p6. No, you only fill it if you need to keep going. Okay. So for this one, we only needed 8 total electrons. So we would stop at 2p4. And so that 2p sublevel, it just wouldn't be totally full. So that's what oxygen's configuration would look like. There is a shortcut. Okay. They're called abbreviated electron configurations, and they're also sometimes called noble gas configuration. And so what they do is they allow us to use a noble gas to shorten the configuration, because as you go down the periodic table and you have more and more atoms that have more and more electrons, they're getting bigger. These configurations, they start to get pretty long. Like this is rubidium and it goes all the way to 5s1. And so scientists are lazy. And so they're like, let's come up with a shortcut, because that's not what, like, nobody wants to be writing that out all the time. So what they did was they said that you could look for your element. So this is rubidium, Rb. So you find that element on the periodic table. And then what you do, okay, and I'm going to draw like a little rudimentary periodic table here. So rubidium is like right about down here. It's in the alkali metals. So what I do is it's on the 5th row. It's on the 5th period. What I do is I go on the row above it. So I go up to the 4th period and I go all the way to the end and I look at what noble gas is at the end of that row. And if you're paying attention, you can already tell that this is a typo, okay? Because they have AR, but if you look at a periodic table, you go to the row above rubidium and go to the end, it's actually krypton, it's Kr. So make sure that you update that. But it's Kr, and so when I do krypton, because krypton ends at the end of the 4th row, so krypton takes the place of everything all the way up to 4p6. And so by writing Kr, by writing that symbol in brackets, that's like substituting for everything from 1s2 all the way to 4p6. So then after that for rubidium, I just have to write 5s1. Now, when we get into topic 3 later on this semester, we tie this more into the periodic table because topic 3 focuses on the periodic table. But for right now, I just want to show you guys. I put a periodic table on here. So this is how it corresponds to the periodic table. And again, we learned this last year. So the S sublevel, remember, can only hold 2 electrons. So the S sublevel corresponds to the first 2 groups because they can hold 1, 2 electrons. So like this would be 2s1 and this would be 2s2. Okay, this is 3s1 and 3s2. The only thing on here there is this picture I'm showing you right now. They did helium the wrong color. Helium is actually part of the S block because it's 1s2. Okay, hydrogen is 1s1, helium is 1s2. The P block is over here, this green area. It's groups 13 through 18 minus helium. Helium's not in it. And if you notice, it's got 6 columns in it because it can hold up to 6 electrons. So like boron would be 2p1, carbon is 2p2, nitrogen is 2p3, all the way to neon would be 2p6, okay? So all the noble gases are always going to end in something p6 because their P sublevel will always be full. And because of that, we know that they're stable. They have 8 valence electrons because their S and P is full. And so they have 8 valence electrons because their S sublevel and P sublevel is always full. So because they're stable, that's why we use the noble gases in the shortcut. And so we know that they're always going to go to something P6. So for the example that we looked at, krypton, because it's in the 4th row, the 4th period, it ends with 4p6. So we can substitute Kr in brackets for everything to 4p6. And then I just have to write what comes after 4p, which if I go back up and look at my little diagonal rule, after 4p is 5s, and rubidium would only need 1 more electron. Okay, so it's 5s1. So they want us to do the abbreviated one here for aluminum. And aluminum, here's the full configuration, goes all the way to 3p1. So what I would have to do is on a periodic table, find aluminum. Aluminum, it's in the 3rd period, the 3rd row. So if I go, the row above it is row 2. And the noble gas at the end of that row is neon. So I would put Ne in brackets. And that's a noble gas, and it's on the 2nd row. So that means that's going to take place of everything up all the way up to 2p6. Okay, because since it's a noble gas, remember it has to end with something p6. And so it's that 2p6 part of the configuration. That's where it would end. So then after that, I would just have to write 3s2 and 3p1 for that one. Okay. So you guys, you have some practice that this is what you'll do for your assignment for, it's not due till Friday because I'm going to have you do both parts at once. But you have practice writing the full and the abbreviated configurations for some of these elements, some of these atoms. What I want to do really quick before we're done is I want to talk about this because this is going to be new information, okay? The electron configurations of ions, okay? When you're doing ions, okay, remember they've lost electrons, all right? So what you have to think about is you have to think about, well, what did their configuration look like before? So for example, if I was just going to do, I'm going to do this first one as an example on here. So if I have sodium, if I just did the element sodium that was neutral atom, it's not a sodium ion. Sodium has 11 electrons normally. So it would be 1s2, 2s2, 2p6, and that gets me to 10. And then after 2p comes 3s, and since I only need to get to 11, it would end with 3s1. So this is the configuration for the atom of sodium that is neutral. When it has this +1 charge, remember, positive ions, that means they have lost electrons. So all of the metals that form positive ions, they will lose their valence electrons. Valence electrons, if you remember, those are the ones in the highest energy level. Okay, remember that these numbers in the front, these are representing our energy levels. So the highest energy level sodium has is the 3rd energy level, and it has 1 valence electron in that because it's in the S sublevel. So when it becomes this ion, this Na+, that goes away. And so to write its configuration, it's just 1s2, 2s2, 2p6. That's it. So what you're going to notice is all the configurations for any of these ions, they're all going to look like noble gases. They're always going to end in something S2, something P6. because the whole goal of all of our atoms is to become stable, and they become stable by losing or gaining electrons to become like a noble gas. So when you're doing these, think about the fact, start off with what would your regular element look like, and then if it's a positive charge, it's going to have lost valence electrons. If it's a negative charge, then it will gain enough electrons to complete that P sublevel and get to something P6. Okay? Yes. 2 minus. It's going to gain 2 electrons. You add 2 more electrons. Because normally sulfur will end with 3p4. So when you do the S2 minus, it'll end with 3p6. Okay, so here's the little catch here. When you have your elements in the D block, so these are the transition metals, and we only really need to know the first row of the transition metals, which is scandium to zinc. They lose their 4s electrons first, and that's because if I go back up here to that little diagonal diagram, okay, remember I told you that after 3D, they kind of go out of order. I'm sorry, after 4s, they go out of order, because after 4s, you go back down and you do 3D. So when you write them, okay, for example, if I was going to do, let's say I'm going to do scandium, okay, I'll just do that one because that one's first. Well, actually, they have nickel in here. Let's do nickel. So if I was going to do nickel, nickel has 28 electrons. So it would be 1s2, 2s2, 2p6, 3s2, 3p6. After 3p comes 4s, so it'll have 2. And then after 4s comes 3d. And so nickel is 28, so it'll have 1, 2, 3, 4, 5, 6, 7, and it'll have 8. 3d8 is where it would end, okay? So if we just did the element nickel, just Ni with 28 electrons, this is what it would look like, following the diagonal rule and all of our rules. When it loses, it becomes an ion. Notice it has a 2+ charge. That means it lost 2 electrons. Okay, you have to look. Remember these big numbers in front. These are my energy levels. And even though it is not written last, the highest energy level is this one right here because it's a 4. Okay, so that's where you have to be careful for those elements that are in that first row of the D block, which is scandium to zinc, because when they lose valence electrons, they're always going to lose the ones from 4s first. Because 4s, even though it's technically further out because it's in the 4th energy level, transition metals do this weird thing where the D orbitals, the D sublevel, those electrons actually have higher energy even though they're a lower energy level number, okay? So for something like nickel, it would lose the 4s. That's what it would lose. So if I rewrote it for the ion, it would be 1s2, 2s2, 2p6, 3s2, 3p6. The 4s would go away, and then it would just have the 3d8, okay? And that goes back to the fact that you got to look at these numbers that represent the energy levels, because they always lose the highest energy level where the valence electrons are. And so you have another one that you can practice on here for manganese, but it's the same concept. Okay, it's going to lose the ones in the 4s, and then the 3d electrons will still be in the configuration. The last thing, really quick, there's 2 exceptions to the Aufbau rule. Okay, copper and chromium. Okay. For copper, it's got 29 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Okay, that's how you would write it if you were following the Aufbau principle. If you were following those rules, you would write it like this: 4s2, 3d9. That gives me 29. However, if you look at what the D would look like, that means that we would have something like this. We'd have this last orbital in the D would be half full because it will only have 9 electrons. And that's actually less stable than another option. So our electrons, they're always going to want to be stable. That's their number one goal. So most of the time following these rules means they're stable, but at a couple exceptions, they're not. And copper and chromium are those exceptions. What will happen is instead of 4s2, 3d9, it will be 4s1, 3d10. Okay, so that changes. And so because what happens is it'll fill this one, and then the 4s will be half full. It is more stable if the s is half full rather than having one of the orbitals on the D sublevel half full. Okay, chromium, same thing. It's got 24. So it'll be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4 is what you would think it would be. But again, it doesn't do that. It half fills the 4s, so it gives 4s1 and 3d5, because similar to copper for the 3d, it's better for all 5 of its orbitals to have 1 electron than for that last one. If you only had 3d4, that last orbital would be totally empty. So what happens is the 4s, it gives one of its electrons away, and it fills this, or not fills, but it gives one to this last d orbital, so that all of them are half full. Because it's more stable for all of them to be half full than for one to be totally empty in that d orbital. Okay. The last part here is really just representing those orbitals in the boxes. And it's exactly what I've been doing. You draw those up and down arrows. You follow the rules to pair them up. Okay. You can abbreviate them just like with the electron configurations. All right. And that's pretty much it for today. So I'm going to go ahead and stop, because that is our bell. And I will see you guys on, what's today? Tuesday, Thursday, and we will kind of recap today, because I know it was a lot. And